Hello everyone, my name is Hoeijmakers. Thank you very much for joining me on the first day of this e-conference. I'm currently a postdoc at the universities of Bern and Geneva, and I will start a lecturer position at Lund Observatory after the summer. I have a presence on Twitter as well as GitHub, where some of my codes are in the process of being made publicly available. Today I would like to tell you a story about titanium and vanadium in the atmosphere of the ultra-hot Jupiter WASP-121b. In this talk, I'll focus on what we can learn from atmospheric chemistry using high-resolution ground-based spectroscopy and the cross-correlation technique. This talk is based on a paper that was recently accepted to ANA, and the accepted version is present on the archive. I'd like to give a big shout out to my co-authors, especially Julia Seidel, Lorenzo Pino, and Daniel Kitzman, who really enabled much of this work. The things that I will talk about form only a small section of the paper, but an important part with profound conclusions. Over the past year, a lot of work has already appeared on this planet, but because of lack of time I can't really mention most of it, but I suspect that other speakers might talk about this object as well, and hopefully cover some more ground. WASP-121b is a transiting ultra-hot Jupiter that orbits a star that is a bit earlier than the Sun. It is inflated, and it has a day-side temperature of about 2700 K. This planet has been observed extensively with HST, and the story that I would like to tell you starts with this transmission spectrum. It was observed by Tom Evans over several transits, with STIS and WIFC3 in various modes, leading to a transmission spectrum that shows a lot of variability from 0.3 to 1.6 microns. Some of this variability is common in hot Jupiters. For example, there is a strong slope towards near UV wavelengths and an unmistakable water feature near 1.4 microns. However, there is also this banded structure that has been proposed to be explained by vanadium oxide absorption. To interpret the spectrum, you may try to fit a model to retrieve, for instance, the chemical composition. This is work by Tom Evans from 2018, which shows that when you assume chemical equilibrium retrieval models, you have a hard time to reproduce some of the variability, and in particular the slope. They propose the SH radical as a possible disequilibrium near UV absorber that could be responsible for it. If you do a free chemistry retrieval, you can reasonably explain the spectrum, in which case you find that you need to have a VO abundance that is much higher than the TiO abundance. When I first saw this, I was surprised, because normally speaking, you might expect TiO and VO to occur together, and TiO is normally taken to be the stronger absorber, as it is in cool stars. In high-resolution spectroscopy, we've had quite a long history in trying to find TiO, and I've written a paper about this. So why would VO suddenly be dominant? And if it is, then what happened to TiO? To explain this scenario, Tom Evans proposed that TiO might be missing from the spectrum because it has rained out in what's known as a cold trap. If the temperature in the atmosphere dips below the condensation curve of a species, it will form droplets or grains and rain out towards the deeper atmosphere. It turns out that at all relevant pressures, TiO has a slightly higher condensation temperature than VO does. In Bern, we model equilibrium condensation, which is work by Daniel Kitzman. And here I plotted condensation curves of Ti, which is expected to first condense into calcium TiO3, and vanadium, which is expected to condense first as VO. You can imagine that if the temperature is high, you'd expect both TiO and VO to remain in the gas phase and be visible in the transmission spectrum. If the temperature is too low, both of them will have rained out. So the observation that you'd have VO but not TiO can be interpreted as that at the location of where this cold trap is happening, whether it be on the terminator or the cooler night side, the relevant temperature profile should be bounded by these two curves. My collaborators in Geneva had observed 3 transits of this planet with the HARPS spectrograph, so we decided to make some models of what the high-resolution spectrum could look like. Here you see 3 examples at 2 temperatures, with and without TiO opacity. The yellow sawtooth-like bands are TiO, and the weaker VO bands in the green model are only visible when TiO is switched off. The other thing you see is that there is a lot of line absorption by atoms, and this fitted well into our existing efforts, which were to find metals in the transit spectra of ultra-hot Jupiters. These models assume hydrostatic and chemical equilibrium, and we use them for the purpose of model comparison, which I will show in a second. So we constructed a range of cross-correlation templates of all sorts of species that might be significant absorbers. There are lighter species which tend to have strong doublets or triplets. There are transition metals which have very rich spectra, iron here is a usual suspect, and also molecules where we searched for TiO, VO, SH, and water. I choose not to delve into the cross-correlation technique in the interest of time. The short summary is that we use these templates to measure average absorption line profiles in the rest frame of the planet, while rejecting such absorption in the stellar spectrum. This is possible because high-resolution spectrographs resolve the orbital velocity of the planet as it goes through transit. The result is that you get these average 1D line profiles, and this is our detection of iron in WASP-121b. If you don't know the orbital parameters of the planet, you can try various values for the orbital velocity, and then the signal can be recovered from this velocity-velocity diagram on the top. Essentially, you can see the 1D profile on the bottom as a horizontal cut through the top diagram when assuming the correct value for orbital velocity. Something to note is that we can do model comparison. The dashed red line shows the signal of the 2000K model I showed earlier that we artificially injected into the data at the start of the analysis. And you can see that the signal that we detect is much deeper than what we might expect using the model, which shows that the planet's atmosphere is inflated. I can't spend more time on the cross-correlation technique, but I made a video recording to explain it further if you're not familiar with this and would like to know more, which I've put on my website, and I will also share it on the chat or on Twitter. These are the results of our survey. We detect a whole range of species, including magnesium, chromium, iron, but also vanadium, calcium, and nickel. We do not detect any molecules nor ions, which are not shown, but for the purpose of our story, I'd like to focus on these four guys. And I would like to draw your attention to how the data in blue compares to the two models that we inject. We don't detect TiO, even though we expect to be capable of doing so if it is there. At the same time, we don't see VO, but because its bands are relatively weak, we wouldn't expect to anyway. On top of that, it is known that the VO line list is likely not accurate enough for application of the cross-correlation technique, but even if it was, we wouldn't have detected it. There is a study led by Stephanie Merritt which goes much deeper into this. But look at the atoms. We detect vanadium while we do not detect titanium, and this looks like the story from HST where VO was detected but not TiO. Also, we see that Ti is expected to be a weaker absorber than V to begin with at 2000K, and this may be unexpected if you know that at higher temperatures Ti is usually dominant because it is 10 times more abundant in the universe. To explain this, here is a plot that shows the equilibrium chemistry of all titanium and vanadium-bearing species. The vertical axis shows atmospheric pressure, and the horizontal axis shows abundance. It appears that at 2000K and 20 times solar metallicity, the abundances of titanium and vanadium almost exactly overlap. This makes vanadium a stronger optical absorber because it has an extra electron in its outer shell that is capable of making electronic transitions. We also see that at this temperature, TiO and VO are important reservoirs of titanium and vanadium, much more so than the individual atoms. But what are these dioxides? Gas phase TiO2 is expected to be half as abundant as TiO, and VO2 is even more abundant than VO in chemical equilibrium. So my first question when seeing this plot for the first time was, what are these species? They are superabundant. Do they have spectral lines? Do they have strong bands like TiO and VO do? And if so, we should be including these in all of our model spectra of hot Jupiters. I've searched for literature on these, and I welcome your pointers here, but as far as I could tell, the exoplanet literature was very thin. All I could find was that in some variable stars, these molecules are known to cause bands in the near infrared. But the dioxides are a bit of a sidetrack. Let's go back to the story of condensation. The picture now is that because we don't see any TiO, we conclude that it has rained out. If a species gets depleted from the gas phase, chemical equilibrium will try to compensate by creating more of that species at the expense of all the others. So if TiO drops out, all the other curves will collapse as well. The entire titanium reservoir will end up rained out in the deeper parts of the atmosphere, and unless global circulation can mix it back up, it will stay trapped there, and this would explain why we do not observe TiO. Condensation does not affect any of the vanadium-bearing species, which is why we can still observe atomic vanadium even though we don't have the sensitivity nor the line list to observe VO with this cross-correlation technique. I will now leave you with the main conclusions from our paper, which covers a lot more than what I could talk about. I would happily like to take questions, both about what I discussed just now, as well as the rest of what we described in the paper. Thank you very much for your attention, and I hope that you have a very nice day.